All right, so we are on 7.4, which is basically all things matrices that go along with systems of equations. Okay, so first off is what even is a matrice? So a matrice will look like this. And we'll have terms throughout the middle of this. So they're always spaced out row by column. So when you talk about the dimensions of one, you will talk about those dimensions referring to them as row by column. So when we talk about specific terms within this matrice, such as maybe this first one, we label it by row column. So this is my first row, my first column, so this would be A11. Moving over, this is still my first row, but my second column, so it would be A12. My next one would be A13 because I'm still in my first row, but that's my third column. So now if we work our way down this first column, we are now on row 2, column 1, so it would be A21. Row 3, column 1, so it would be A31. Okay, so I will not particularly reference any of these terms by their term name or term number, but in the SAT or AccuPlacer or something like that, you might see that happening. So just being sure that you can reference these based on their row and column number will be super helpful for you. Another thing, let's label this by its row and column because there are 3 rows and 3 columns. This would be a 3 by 3 matrice. Okay, when you have same rows as you do columns, that means that it is actually what we call a square matrix. Okay, and another obvious way to tell that is if it looks like an actual square. If it looks like a rectangle, probably because it has less rows than it does columns or more columns than it does rows. Okay, so those are the kind of just little tiny basics about these. So if I had, so just a couple other matrices up here. If I wanted to label the following. Say, okay, let's say we had the following 3 different matrices. I want you to try to label these by their dimensions. So this first one, I have 2 rows, 2 columns, so it would be a 2 by 2 matrix. The next one, I have 3 rows, 1 column, so this would be a 3 by 1. 1 row, 3 columns, so 1 by 3. Okay, and out of all of these, this is my only square matrix because it was the only one with the same rows as it has columns. So for what we're dealing with, particularly in this one section, we won't have to use their dimensions as much, or really, we won't be talking about dimensions a ton. Once we move forward into 7.5, and we're adding, subtracting, and multiplying matrices, then you will end up having to use their dimensions a lot in order to find its next new matrix. Okay, so all we're doing kind of in this last bit of the section, or this last bit of the chapter, is learning how to use matrices and in what ways can they be helpful to us. So what we just got done talking about in 7.3 was solving systems of equations when we had more than 2 variables. So for instance, we had 3 equations with 3 variables x, y, z, and we solved them through Gaussian elimination. Row by row, we would cancel them out until we got a z value. We can do that exact same thing with matrices. And in my eyes, this version is actually a little bit easier. I think it ends up taking the variables out of it and leaves you with just numbers. So it's a little bit easier to see how things can cancel out, maybe a little less writing even. I would prefer this way. And I know many other people also would kind of feel that same way and having this as their preference. So the first thing in trying to use matrices when we're trying to solve systems of equations is we first have to be able to write that system of equation as a matrix. So let me give you the following. X minus 2y plus 3z equals 9. Negative x plus 3y plus z equals negative 2. And 2x minus 5y plus 5z equals 17. Okay? So what we do is we put this into what we call an augmented matrix. So we draw up this matrix. All right. Because it's augmented, I put this line with just one last column on the other side of it. So when we draw up this augmented matrix, this first whole column is our x value. The second column is our y. The third column is our z. Then this line here is representing the division line between our coefficient matrix and our constant matrix. Coefficient being coefficients to all the variables. So this line can almost act as the equal sign, and all of our constants come over here. So in other words, we have just the numbers or the constants going on that right side of that line. So what I'm going to do is I'm going to pull all of the coefficients. So I'm going to go line by line. First line, I have a 1 for my x in front of that. So the coefficient there is going to be 1. So in that first row, first column, I'm going to put a 1. Next coefficient is a negative 2. So I'm going to put negative 2. Then I have a 3z, so that coefficient is 3. Lastly, equals 9. Okay, so you are taking out all of the coefficients, leaving behind all of the variables. Next row, negative x, so negative 1, 3y, so 3, 1z, so 1, equals negative 2. Very last equation, 2, negative 5, 5, and 17. Okay, so this is what we call our augmented matrix. By the end of it, when I take away the fact that I know what these rows stand for, I should have a matrix with just numbers, no variables, that allows me to have an easier time trying to solve this systems of equations. So just like you could before when you were dealing with just these equations, I could do like row operations by taking maybe the first equation, adding it to the second to get a new 2. For instance, that notation might have been 1 plus 2 to get a new 2. And I would use that notation, okay? Now what we're going to do is we're going to use what's called row operations. Row operations can be in basically 3 forms. I can switch rows. So let's say I wanted to switch row 1 and row 2. I could flip-flop them if I wanted to. I can multiply a row by something and add it to another row. I can divide a row by something. So I can multiply, like if I want to divide by 2, I can multiply by 1/2 to divide by 2. I can do whatever I want with these as long as it's kind of within those 3 parameters. The only big thing you cannot do is multiply by 0. Obviously, if I multiplied any of these by 0, I'm going to get 0 equals 0, which is infinite in many solutions. We're not dealing with that. You cannot multiply by 0. Anything else is fair game. So the goal here is to solve for z, just like it was in our normal equations. We were trying to just get z by itself. We did that by getting rid of our x, and our y. So in this case, with this matrix, I want to get rid of this 1, 2, and negative 5. In other words, I need a 0 in this corner. All this corner needs to be zeros. So in order to do that, my first step is going to see how can I get rid of x's first. So right off the bat, I see, well, if I add row 1 and row 2 together to even do 2, I can get a 0 right here. that notation is going to be row 1 plus row 2 to get a new row 2. So one thing that's important for you to understand is I do not need a ton of work off to the side for these. If you don't show your work, it's going to be hard for me to catch what kind of mistake you're making. But I do want you to just understand, I do not need to see you adding these two off to the side. For your sake, I'm going to, for these first couple times, to make sure you know what I'm doing and how I'm doing it. But as we get going and we get more steps with these, we're not going to quite do all that work off to the side. So I'm taking 1, -2, 3, and 9, and adding it to -1, 3, 1, and -2. So we're adding straight down. These cancel to give me a 0. -2 and 3 is 1. 3 and 1 is 4. 9, -2 is 7. Okay, so now I can write that in my new matrix. Notice in this new matrix, everything else is going to stay the same. So my row 1 is not changing. My row 1 will still be 1, -2, 3, and 9. My row 3 is not changing. That's staying the same as 2, -5, 5, and 17. What is changing is my row 2, and it will now be 0, 1, 4, and 7. Okay, so now I want to see how can I get rid of this 2, right? We work left to right. And I want to also remind you, if you're comfortable with it, you can always do 2 steps in one. So to get from my original matrix to this one, I also could have done some row operations that got rid of this 2 at the exact same time. I can do multiple row operations at once as long as they are not contingent upon each other. If I needed row 2 to do something with row 3, I can't do that because row 2 is being messed with. Okay, the next thing I want to look at is getting rid of this 2. So I know using row 1, I can multiply row 1 by -2, add that to 2 to get 0. So my row operations would be -2 times row 1 plus row 3 to get a new row 3. Okay, writing that work off to the side here, I need to take row 1 and multiply by -2. That would be -2, +4, -6, and -18. Added to 2, -5, 5, and 17. Cancels to 0, and -1, -1, -1. This is my new row 3. Okay, I'm going to continue that row 3 way over here. Keeping in mind my row 1 is still the exact same that it was. Okay, so it's still 1, -2, 3, 9. My row 2 now is still 0, 1, 4, 7. Bringing back now to my new matrix, I have 0, -1, -1, -1 for my third row. So in other words, I have one big last step to do, because that one big last step is to get this -1 to be a 0. So this last step is actually a really obvious and easy one. I see, well, I have a -1 to +1. So if I just simply take row 2 plus row 3 to get a new row 3, I can get that down to 0. See if we can squeeze all these columns in. Okay, so adding these up, 1 plus 1 is -1, sorry, 0. 4 plus -3, goodness, 4 plus negative 1 is positive 3. 7 plus negative 1 is 6. Okay, so that new row 3 is the only thing that's going to be new. So I can still have all my other same rows of 1, negative 2, 3, 9. None of my markers seem to want to work. Here's a good one. And 0, 1, 4, 7. Okay. So I did what I needed to. I got my lovely little triangle of zeros. In this case, the last thing is going to be completely extracting this. So generally, one last thing I want to do is see reduced row echelon form, so 1, 1, 1. That is exactly what I would love to see in this case. If I can make that happen, let's do it. It's one more extra step. You can always just solve for that z once you extract it. So that last step would just simply be taking row 3 and multiplying it by 1/3. Why 1/3? Because multiplying by 1/3 is the same thing as dividing by 3. To get this to a 1, I'd need to divide by 3. If we'd done that, again, it would be 1 and 3. Sorry, 1 and 2. What am I thinking? 1 and 2. Okay, and that would typically be that nice last step for me to have all 1s and my triangle of zeros, and now I can extract. Again, if you had left that 3 and 6, not that big of a deal to me. But if they do ask for row echelon form, this is row echelon form with those leading 1s. So when I go to extract this, I have to keep in mind that these are my x's, y's, z's, equal sign, a number. So bringing this back up, I have 1x minus 2y plus 3z equals 9. And then no x's but 1y plus 4z equals 7. Very last equation, no x's, no y's, 1z equals 2. So this is exactly what you would always want to get when you are done solving these multivariable equations. When you are done, that is exactly what you would want. Our matrices is what allowed us to help us take all the variables out of that, focus on just the numbers, and solve to get these solutions here. So you will still have to back substitute. While I have my z value, I still need my x and my y. So back substituting, I can put 2 into this second equation. It will be y plus 4 times 2 equals 7, giving me y plus 8 equals 7, or the fact that y equals -1. Back substitute both -1 and 2 into my first equation to get x minus 2 times -1 plus 3 times 2 equals 9. X plus 2 plus 6 equals 9, or x equals 1. Solutions to this were 1, -1, and 2. This is actually an example that we did do with our first round 7.3. And you did actually solve this one just through Gaussian elimination with these systems of equations, variables all included. So same exact answer. One, we used Gaussian elimination through actual elimination. The next one, we used it through a matrix. So both ways, I will have you try maybe one of each of them on the test or the quiz. But again, truthfully, I think that these with this matrix is a lot easier to solve for and kind of see how you can solve these, especially for some longer ones. But if you like the other way better, again, just kind of giving you some different options here. All right. There's lots more I could show you, but in this case, truthfully, I think one is going to be a good place to start at. And if we need to make more videos with some more, we can go ahead and do that, okay? But just another tool that helps us solve multivariable systems of equations.